Welcome, everybody. We'll be hearing about awkward arrays in Dask from Doug Davis. Doug has his PhD in experimental particle physics from Duke. You might know him from the Atlas collaboration. So last year, he joined Anaconda Inc. as a software engineer in Anaconda's open source team, which works on various pieces of the PyData ecosystem like Numba, HoloViz, Jupyter, Dask, and more. Doug now focuses on the Dask ecosystem, developing such tools as Dask histogram, which is delayed distributed boost histograms, and Dask awkward, which we'll be hearing about now. So everybody, welcome Davis, and you can go anytime you're ready.
Great, yeah, thanks, Jim. So yeah, it's nice to be talking to an audience of particle physicists again. Yeah, before I get started, I just wanted to thank Jim again and some of the other colleagues working on Dask awkward. My colleague at Anaconda, Martin Durant. There's also various other members of IRIS-HEP that have been participating in discussions and meetings we've had going on, like Angus and Ayana. So yeah, thanks to everyone that's been helping with awkward arrays in Dask. And so yeah, I'll go ahead and get started. We'll start with a quick outline, pretty simple outline. I know that Dask has been discussed in this venue before, but I think it'll be good to have a Dask overview. We'll start giving a high-level kind of introduction to Dask, just to get the foundation set. Then I'll talk conceptually about Daskifying awkward. So Daskifying something is actually kind of a general thing, but I'll talk specifically about how to Daskify awkward. And then the last thing we'll do, we'll spend a good bit of time with a notebook demo. Okay, so we'll go ahead and jump into our Dask overview here. This is one of my favorite graphical representations of what Dask does. So the two things that Dask does is create and execute task graphs. So this little graphic here has a task graph and then the execution of that task graph. So there are nodes in the graph, and obviously connections between the nodes, and the colors changing show tasks finishing and becoming dependencies to later tasks. So this is just a very complete but high-level picture of what Dask does. It will generate this graph and provides the engines for execution. So a few more details about that. So how does one create the task graphs for Dask? So this is the collections side. So on the left side of this diagram, we have the various Dask collections. So there's Dask array, which is a way to operate in a NumPy style to generate Dask task graphs. Then there's Dask data frame, which is a pandas style way to generate task graphs. There's also Dask bag, which is kind of a functional programming, the map reduce paradigm on like Python iterators. Then there's Dask delayed, which is a way to take generic Python code, any Python code, and turn it into something that can be lazily evaluated with Dask as an engine. And then there's also like Python's futures support in Dask. So the next step in the middle here is the task graph. So there's the collections API, which, like I mentioned, allows you to program in the same style as these kind of foundational PyData libraries like NumPy and Pandas to create task graphs. And then there's, on the right-hand side, the schedulers, the execution engines. So Dask started out as a way to do an out-of-core computing. So if you had a data set that didn't fit in memory on your laptop, you could use Dask to execute code over your data that didn't fit in memory in chunks, so that you could avoid running out of memory. Then with the during the evolution of Dask as a project, which started at this point about 7 years ago, the distributed engine was created. So that way you could spin up a cluster of 100 machines, with a cloud provider, and then You could do distributed computing on the cloud with Dask, with Google or Amazon or a local batch cluster or something like that. So really the final thing I'd like to say here is repeat myself again. Dask is a way to create task graphs, and it also provides the execution engines. Okay. Now, what we'd like to do is add another collection. Down here in the bottom left, just created a new Dask awkward collection. So that's what today is about. We'd like to add to this list of collections with support for awkward arrays. Okay, so now I'd like to say a few words about what a Dask collection actually represents. So the collections API, it's an API for creating tasks. It's Dask task graphs at core are really just Python dictionaries. So Dask graphs map unique keys to computations. Like I said, it's a dictionary. So in this case, I'm looking at a dictionary that has three kind of steps to it. And each step, what I want to do here is call numpy's ones function. So just create an array of ones, but I want to do it 3 times 100 elements each. So this is an array that is 300 elements, but chunked into three equally sized components. So you could write this by hand, like it's written here. I have a key. One's my 0th partition, one's my 1st partition, my 2nd partition. And those are my unique keys. On the right-hand side, I have a callable and the arguments to that callable. So it's kind of Lispy. And this is a by hand Dask task graph where the lazy computation is represented by this tuple on the right, which is the callable and its arguments. One does not want to write this by hand to do distributed computing. So Dask provides this API. So you can call Dask array.ones at 300 elements long, chunked into pieces in 100 element pieces. So this is what the collections API provides, a high level API for writing code in the same style you would with NumPy, but here with an additional argument to define how it's chunked. But really Dask aims to be familiar to users of the PyData ecosystem to do distributed parallelized computing. So just to take this one step further, now let's do an additional operation. So we'll create our array of ones and then let's add them, add it to itself. So in this case, we have the same task graph as before, but here I've appended something Dask does. It creates a unique suffix for these steps. So we have our same task graph as I showed in the previous slide, but upon adding them, this is how one builds a task graph in Dask. Well, this isn't how one should do it, but this is how a task graph is built in Dask. As you do steps like x equals, Dask array.ones, then y equals x plus x, this is what's happening in the background. No computation is occurring. You're just building a task graph where the keys from some previous step become the dependencies in a later step. And this is how how Dask builds itself a task graph. So I just wanted to show these. This is the most detailed I'll show here, but I think it's good for wrapping one's mind around how Dask accomplishes what it's trying to do. So it just builds what really at its core are Python dictionaries to create these task graphs. Okay, so how does one Daskify awkward? So here's an awkward array. We have some X's and Y's here, and an array of nested records. We have variable length going on here, and in each case, there's some variable number of records, the braces, in each element of the array. And then within these records, there's some variable number of Y's. So we have an awkward array. The shape inside these nested layers is changing. We obviously can't use any of the rest of our PyData stack. We have to lean on awkward array for this. So how does one Daskify this style of array? It's actually quite simple. We just partition it along the outermost dimension. So in this case, the outermost dimension has just these variable length arrays inside of the record. So we just slice it across along that outer dimension. This at the most basic level is a complete description of how one Daskifies awkward. We're just slicing along, or partitioning, sorry, along the outermost dimension. So, the last thing I'd like to say conceptually about this is that this is very similar to data frame, to Dask data frame in the way that it's partitioned. So if you have familiarity with Dask, or if you've used Dask data frame before, this should feel natural to use Dask awkward, where on the left side, Dask array chunks along however many dimensions your array has. In the case of Dask awkward, we don't have all of the knowledge about the inner dimensions, always the variable length inside along the inner dimensions. I mean, that could be changing. We don't have the ability to partition there because we don't have complete information about the shape there. So it actually, it simplifies the problem. We can, such that we really only can, since we can only partition along the outermost dimension, it actually simplifies how we do it a little bit. So partitioning along the outermost dimension is the way in which we Daskify awkward. So at this point, let's talk a little bit about the scope and some things that we currently have in Dask awkward. So I'd like to, this won't be the first time I say this, but Dask awkward is in development. But we'd absolutely welcome curious users, folks that want to kind of live on the edge, so to speak. So some things that are currently supported in our new Dask awkward collection. So element-wise operations. So this might make you think of NumPy ufuncs. So you can call numpy.sign on a Dask awkward array, and that will work. Many of the slicing operations or Python's get item operations work. So if you have an array that has a foo field, x.foo, or string get item, the string slice, that will work. Selecting a list of strings will work. Using an empty slice to grab all elements along the outer dimension, but then give me the 0th component on the first inner dimension. That's the last example there. Operations like that work. Next, so some row-wise operations work. So for example, doing like a Boolean selection, and also some inner axis operations, like reductions and structure functions, which is also included in the next bullet, for some things that are partially supported. And also to and from some other Dask collections. So you can convert to and from Dask arrays or to and from Dask's delayed objects. So these are, that's a list of things that are currently well supported. Next, a list of things that are in motion or planned. So obviously awkward has a wide range of let's say like top level namespace functions. So things like reductions and structure functions. So things like min and max and mean, or counting the number of elements, things like that. Some of these are supported, but there are there are arguments to these functions, and not so for example, the axis argument, you could apply for some of them, axis 0, axis 1, or axis none. Some of those operations are not supported yet. So there's a if you are eager to jump in and use Dask awkward and you execute something that's not supported, you will get a not implemented error at this point. But like I mentioned, these are things that are in progress. There's some IO capabilities. So as of right now, we have some simple JSON reading that's implemented to create our collection. Work with Parquet is in progress. This being a particle physics venue, root is being experimented with at this point. There's a proof of concept, but it's there's not official support in the library yet. To and from Dask data frame is something that's planned. Another thing that we've experimented with is Numba. So obviously awkward has Numba support, so we absolutely plan to be able to run Numba functions as part of a Dask awkward task graph. Something else that's planned is improved Jupyter support. So one of the nice things about Dask in general is if you're using Dask in a Jupyter notebook or Jupyter lab, there are some nice kind of visual tools for visualizing what your collection conceptually looks like. So that's something that we have planned to support as well. So this is an outline of some things that are supported, some things in progress, some things we plan to support. But this being something that's in development, we absolutely are eager for feedback from folks who are starting to tinker with it. We'll absolutely listen to what folks are looking to have. So at this point, I'm going to go ahead and jump over to a live demo. The repository where this demo lives is here at my GitHub, Douglas Davis /dask-awkward-demo. I'm going to go ahead and pull it up locally here and run through it. But that link is there for for reference if you'd like to pull it up yourself later. So go ahead and jump over. Okay, so here we have a Jupyter Lab instance. And on the right-hand side, I've got two empty panes here. I'm actually going to be using Dask's lab extension to see Dask kind of, doing its thing, kind of in action. So we'll watch the task graph get executed. So starting here at the top, I have a few imports, and in order to use the Jupyter Lab capabilities, I'm going to start a Dask distributed client, which discussing that is a bit beyond the presentation here today, but it's just one of the execution engines for Dask. So I'll go ahead and spin that up. Okay, with that, my cluster setup, which is just a cluster running on my local laptop here. Let's talk about the toy data set that we'll be playing with. So this is a data set that I know Jim has used in demos before. We have Higgs to 2Zs decaying to muons. This is just a simulation sample. So as I mentioned, the current IO support, we have support for from JSON. But before we load this data from JSON using Dask Awkward, I'm going to just take a quick look at it, and ignoring the existence of Dask, like eagerly loading some of this data just so we can take a look at what we're playing with here. So I'm going to load one file from this data set. So here's this is just an awkward array with some obvious awkward structure to it. So let's just look at one entry here. So we have some run information, luminosity block, missing ET, but what I'm going to focus on today are the muons here. So in this case, we have some muons. Here's our list of muons. Each muon has, it's 4-vector here and a charge. So in this, the 10th element here, we have 2 muons. If we look at the 0th element, let's see, here we have no muons. So you can see the awkward structure there. There's some variable number of muons in each event of this data set. It looks like there's some stuff in the chat. A question. Okay, we'll get back to that. Okay, the structure of the data set. We have an awkward data set here. Let's do, still living in an eager awkward land, nothing lazy yet. We can perform some selection here where we limit ourselves to only events that have at least 4 muons. So here we're doing awkward.num to limit ourselves to exactly 4 muons in each event. In this case, we originally had almost 6,000 events in this data set. If we limit ourselves to 4 muons, we can see we drop down to a little over 450. So that's the data set we're playing with. Now let's actually look at Dask. Okay, so I've imported Dask Awkward as DAK. This is our this is what we've adopted as our Dask Awkward import. So I'm going to do Dask Awkward from JSON. Before I do that, actually, I'll show you what's in the data. I just have 50 files here of some compressed line delimited JSON. So let's load that up with dac.from.json. There we go. Let's look at our data set now. So we have Dask Awkward from JSON in partitions equals 50. At this point, we've done nothing with the actual data on disk. We've just, we have materialized a task graph, not an array. So we have a a task graph that has the instructions to load these JSON files off disk. All right, so let's build up a high-level example. This is what we're going to do. We're going to check how many muons are in each of the events. We're then going to do some selection to require that we have exactly 2 opposite sign, or not opposite flavor, just opposite sign. I've written that too many times. 2 opposite sign muons. We will grab events from the original data set that pass that selection. Then we're going to calculate the invariant mass of the muons that we've selected, and finally histogram that value. Very simple particle physics style high-level example here. And we're going to do this all lazily. And I'll kind of show the building of the graph as we go. So the way that Dask awkward connects to awkward is we recreate the API. So ak.num, and recreating that API will have dak.num, but dak.num, instead of actually calculating num, is just going to build the task graph that will use ak.num when we actually want to compute the task graph. All right, so the first step, we'll be calculating the total number of muons. So we do dak.num to create this new step in our task graph. So we have dataset.muons. So this is actually doing two Dask awkward operations. This dataset.muons, we're doing a get item to grab the muons field, and then we're doing a dak.num. So we'll do that. It happened instantaneously. We're not actually processing data. We're just building our task graph. So let's visualize what we have so far. A little small here because we have 50 partitions, but I'll zoom in a bit. So here are the 2 additional steps I talked about, get item and num. So here's a visualization of our task graph. At this point, we have 50 partitions. The same thing is happening on all of them. We read the data, we grab the muons field, and we do the num, we call the num function. So this is our 50 partitions just going all the way across here. Let's keep going. A nice way to visualize the task graph with a little bit more compactly is to visualize the .dask attribute on our collection, which is the high-level graph. And this will actually compress it. We can see every, from JSON, get item, and num happening on all of our partitions here. And a nice feature, this is actually kind of new, we can visualize it with some colors. So if you're familiar with Dask and you know various layer types, you can also color code your visualized task graph. So this is a nice feature of using Dask inside of a Jupyter notebook. You get some of this extra information. I won't go into the definitions exactly of what these layer types are, but it's just parts of the way Dask builds these task graphs. Okay, so now let's look at continuing our high-level analysis here. So now that we've computed the total number of muons, we haven't computed, sorry. We've staged a task graph to compute the total number of muons. Let's keep building by selecting only the events where the total number of muons are equal to 2. Once we've done that, we will require our opposite charge pairs. So then once we've defined our muon pairs, then we'll grab from all events the 0th muon and from all events the 1st muon, add those charges up, make sure they equal 0. And then finally, we'll take our oppo sign selection and apply that to the muon pairs to finally get our selected muons. So let's go ahead and execute that. Again, happen instantaneously. We're not doing anything except building the task graph. So let's see what it looks like now. So now it's a little bit more busy. We've added quite a few steps in task graph language now. So still same thing, loading JSON, getting the muons, requiring the total number to equal 2. Then we're getting the charges, we're adding them, making sure they're 0, equal to 0 here, and then finally selecting them. So this is the construction of our task graph. Jump down a little too far. Okay, now at this point, we want to calculate the invariant mass now that we've done our selection. So we can grab the 0th muon and the 1st muon. So I'm calling them mu1 and mu2. And then we're calling a numpy function to just calculate the invariant mass of this pair. Execute both of those. So now we have a final thing to look at now, just looking at the compact notation or representation here. Lots of steps here in this task graph, all to just calculate the invariant mass. Again, we still haven't executed anything. Then the final step I'd like to execute is to histogram this invariant mass. So Jim mentioned another project that I've worked on since joining Anaconda is Dask histogram. So I'm going to go ahead and import Dask histogram as DH, which Dask histogram is aiming to boost histogram what Dask awkward does to awkward arrays. So distributed parallelized histograms is what Dask histogram provides. So in Dask histogram, we'll just use the histogram function. This is the NumPy-like API. We're going to histogram our invariant mass. We give it total number of bins and a range. And instead of returning arrays, I want it to return a histogram object. So I'll go ahead and do that. So here is our histogram. We have a Dask histogram. It's one dimensional. We're just, we're going to have a distribution of the invariant mass. And so what I'd like to do here, finally look at the last version of our task graph, which now it's going to be, it's got a lot of steps in it. So I actually get a little complaint here that it's a big task graph. So I'll zoom in on it. So we have 50 partitions, calculating the invariant mass on each of those. So this is what we've seen already before from JSON, doing our selection. But now the new step here, these two get items are grabbing the two muons. Then we're using the two muons to calculate, or we're using their 4 momentum components. That's these get items are calling their PT and eta and things, doing a multiply, a subtract, a cosh, multiply. This is all the steps necessary to compute the invariant mass. And finally, the square root. And from there, we do a histone block. So this is the histogram step finally. And then there's a tree reduction to finally collapse onto a single histogram at the end of the day, which in our zoomed in task graph is way over here. Finally, that's the final node in our task graph to give us our histogram. So we can now, what Dask does in the background is it will optimize this task graph. So Dask will detect that a lot of operations are happening on a single node, or can happen on a single node, and it will optimize the graph, and all of those steps to computing the histogram on each block will get collapsed into a single node, and the invariant mass calculation of each partition will all get histogrammed essentially in the same step. And then finally, the tree reduction to get our final histogram. So that's our high-level analysis completely in task graph form. We haven't computed anything yet. So what I'm going to do now is pull in hist so that we can actually look at our final histogram. And finally, we have our first compute. So I'm going to execute this cell. And on the right-hand side, we're finally going to see Dask actually doing some work. There we go. So it happened pretty quickly. It's not that much data. The majority of the time was actually spent here and from JSON. So you can see, I'll zoom in here a little bit in the task stream. So the yellow blocks are from JSON. So this is reading the data off disk, but we can also see that I have 8 processes here that operated in parallel to process these 50 partitions. And every now and then we see some blue here, which is the histone block step. So once Dask has completed one of the from JSON steps in this graph, it will move on to the histone block step. And then finally, one of the later steps we'll see here, if I can grab it, here's hist aggregate. So once it had enough of the histograms on each partition, it started to combine them into the final aggregated histogram. So that's our pretty simple, there's our nice Z mass peak. So that's a simple high-level analysis using Dask awkward. We used a handful of things here, some slicing, some Boolean selection, so then finally feeding it into Dask histogram. So this is a first example of what can be done with Dask awkward. Before I wrap up, I would like to say a final few words about building up a task graph. And how some of the things that we can use to our advantage to help someone on the analysis end. So I'll start with going to Dask data frame world for a second. So one of the things that would be useful for an analyzer is to fail as quickly as possible. i.e. before compute time. So if you've spent a lot of time building up a task graph and you hit .compute and halfway through it fails, okay, you obviously wasted some time. If we could have raised an exception for you while you were building the task graph, that's a little bit of a better user experience. So one of the things Dask, data frame, and Dask array have is they have metadata to be able to give you some information about what your eventual data set, what the structure, what your eventual object, what its structure will be. So I'm going to create a little toy data set into a Dask data frame. This is from Dask's datasets module. Just create a little time series. And if I look at this DDF, my Dask data frame, it has 4 columns, and it's empty. There hasn't been a compute here yet. So this is just an empty data frame. But if I look at the underscore meta attribute here, this is a real Dask data frame that is also empty. But this allows Dask to kind of intelligently stitch together steps in a task graph. So we're trying to recreate that pattern with Dask awkward. So we're carrying around an empty awkward array with the same underscore meta. So here, this is an awkward array that doesn't have any content, but it does have information about the structure of the array. So we can look at its fields. So our metadata allows us to have a .fields component. And then if we ask for the muons part, we can ask for the fields again. So then we know muons have, their 4-vector information. So what this allows us to do is, for example, fail as early as possible if you try to access some attribute that doesn't exist. So here we know energy is not part of this. So because we know the information about the fields, we're not performing a compute step here, but we can still raise an exception before compute time because energy doesn't exist as a field. But then if we ask for PT and ADA, we're not computing here. We just created a new Dask awkward array. But this works. We haven't computed yet. And we know this works because those fields are in our empty metadata. But the last thing I want to show is something that would crash. This is, let's say we skip our step of requiring that we have exactly 2 muons. So now there may be a case where we have 0 muons. So if we ask for, the muons charge, give me every event and give me the first muon, and give me every event and give me the second muon, well, we don't know that inner structure at this point. We don't know if there is even, a single muon in there. So if we create a task graph with this step where we want to make some selection that requires the charge of the first and second muon to sum to 0, we can create that step. It just successfully happened. We've staged a new task graph, but when we call compute, we know the data set has events without muons. So here we crash the compute time. So this is, the final little piece of the demo I wanted to show, that stuff we're working on to make an analyzer's life a little bit easier if we can. So yeah, that's everything I wanted to show today with the slides and this first demo. Like I said, this demo is available here. I'll click on I'll go ahead and pull it up here in my browser. Here's the GitHub repository. So there's a requirements.txt in here, and the data used was here. So you're, please feel free to play with this demo in your own time if you'd like. And with that, yeah, we can just jump over to discussion, have some questions. Yeah, that's it.
Gordon has a question, but let's go in order. And also Kyle, I see, and Michael, and the other Doug. So I'll go in the order that I see on the screen, but I saw Lucas's first. It was raised in chat. Lucas, do you want to say your question out loud? Are you still here, Lucas?
If he have to leave, we may have to read it.
Okay. All right, so I'll just, I saw Gordon next.
Well, I think Lucas still wants his question answered. He put it there, I think, because he was had to leave early for another responsibility. So
Yeah, we can get
maybe
you
Jim,
next
you
time.
could just read it out loud and
Oh,
it could
sure,
get
sure.
answered.
Sure, yeah. So Lucas is asking how, well, he says, writing question as you may have to leave in a bit. Oh, okay. It would be interesting to understand how Dask awkward would mesh with differentiable awkward work that we're doing. In some sense, differentiation is a high-level awkward to awkward transformation. Happy to chat more offline. We will chat more offline. Those particular two cases, not every pair is like this, but those particular two cases I think will mesh well because the what you've seen here is awkward array running in Dask. So Dask is on the outside, awkward array is inside of that. The implementation for differentiable awkward, we're having jacks run inside awkward. So like Russian dolls, right, nested inside. There's no ambiguity about which should be outside of which. So we'll follow up with Lucas about that, but that I think is an easy answer.
Yeah, thanks for answering that, Jim. Yeah, my answer to that was going to be, we'll need to chat offline, yes.
Yeah, right, because you haven't been on this differentiable part. All right, I'll let you answer the next one. Go for Gordon.
Yeah, Doug, that was a fantastic talk. Not just the technical part, the work that's been done, but also I really love the way you were able to, mesh the slides and the notebook demo. I'm gonna try and copy your style there. I have two questions. I think these may be technical, so I apologize. So first of all, as you noted, there's this huge namespace of functions at the top level of awkward that you call like ak.num or ak.count, etc. If I pass a Dask awkward array, will those work, or am I going to have to convert, rewrite all this code that currently uses, ak.count to use dak.count, or change the import at the top of every file?
Yeah, so we very recently discussed this. Martin and Jim and I and other folks collaborating on this. We had a discussion about having a dispatch mechanism in place such that you would not need to rewrite. So if a Dask awkward collection is passed to an awkward function, it will dispatch to the Dask awkward version, similar to NumPy.
Right. NumPy,
yeah.
Right? Yeah, exactly. I know that mechanism is already in place there.
Yeah, so
perfect.
We do have plans for that. Yeah, it doesn't exist today, but we absolutely have plans for that.
The second one was I was just wondering how people were thinking about behaviors in this context. So, for example, the beauty about behaviors is they break down into the much smaller operations, which you are already, it looks to me like turning into awkward Dask operations. But they are a very convenient high level. Like, for example, you had to calculate the invariant mass there. There's already something where you can slap a behavior onto an awkward array and then just say .m, and it will do that calculation for you after adding together the two vectors. It has. Is there any chance that we'll be able to reuse that work that's gone in the community in this environment?
Yeah, so behaviors are, it's another thing that doesn't exist today, but it's something that has come up in our discussions. So it's something with planned support. Yeah, and Nick just mentioned in the chat, it is something that we recently talked about. And at the end of the day, the task graph built from using eBehavior to do that would be the same task graph built.
Exactly.
So it's something that, it's something we have.
They're a very convenient way for an analyst or physicist to write a library of functions on their data set. So it would be wonderful to support them, but if not, there are probably other routes that could be taken. But it'd be a lot of work that potentially would be lost. Okay, and I guess the very final question is, you have this materialized layer that you were showing in the various graphs. And right now that materialized layer is written for JSON. And then I think earlier you mentioned there's an experimental, how do you load it from root? So I guess uproot Dask.
Right.
As one might say. Is it possible to, if there's another data source that will produce a Dask-like arrays, how is it possible for a mere mortal, the user, to write another materialized layer which does the conversion and the loading much the way we saw here from JSON, or eventually we would see from root? Is that, I mean, I know it's all open source, but some things are really hard and some things are approachable.
Yeah. Unfortunately, my first reaction to that would be there's not a well-defined, I'd say, high-level API for creating like custom loaders other than Dask.delayed. So Dask.delayed would be the first place to do that. So I'll just scroll down here to the bottom real fast. You could have a function, so load root, and attach a.
Sorry, I can't see where you're talking. Oh, there you are. Yes, got it.
So Dask.delayed on some kind of load root function, and then there could then be from delayed of something. This would obviously need some kind of input file name,
right?
And this would be the pattern that I think you're talking about.
Okay.
So you could create a function that, without this at Dask.delayed, would load that data immediately. It would be an eager execution, but by giving the delayed
decorator.
Yeah,
okay.
One could, this lazifies this function, and and you could start building like so. Having a the way that, so from JSON, for example, is not implemented like this, but but this is absolutely, I'd say, an entry point to get started with doing some lazy data loading.
Okay, great.
Yeah. And then once that exists, of course, you can tinker from there.
Right. And I guess the things that are missing from there are chunking and other stuff like that. But as a first go, that's not a bad start.
Mm-hmm. It at least lets you start to lay out your foundation for doing lazy loading, and then next step, like you mentioned, would be chunking. And then once you've done that, then you can translate it into your own task graph, if one was interested. But then, as I mentioned, this is things like this type of data loading, for example, is a good example of things that we'd like to hear from folks about, for adding built-in support. Yeah, this is a good example of that.
All right, absolutely fantastic. Thank you so much for the talk. Mm-hmm. Really good to see.
Yeah.
Next question is from Douglas Benjamin.
Thanks for a nice talk. And the questions I have are more about optimizations for data flows and data flow scaling, because obviously, it becomes an issue if you stay within one compute cluster, but if you then try to span across compute clusters. And I noticed that you had the task graph had optimization for compute, but what about the data flows needed for the compute?
Okay, so yeah, this is
because if each node has to process, hundreds of megabytes of data, then data flows become real.
Yeah, absolutely. So this, I'm actually going to go to Distributed's website. I would sadly punt that to the Distributed project. So the Distributed project cares a lot about what you just talked about, Doug, where there's the distributed project is independent of the Dask collection. So these, what you were mentioning of data flow, transferring data between nodes, stuff like that, that those problems have been hit by folks using Dask array, using Dask data frame. So the distributed project there are mechanisms here for when those problems are found, and so yeah, I would, my answer to that here today would be the distributed project is also always in development, and it's something that folks in Anaconda have worked on, but it's not something that I've spent much time with yet. Perhaps I will as time goes on, but there's a lot of activity in this project right now. I will say that there's rapid development. These are problems that people are hitting all of the time, especially as more people are moving to large, distributed clusters. So there's a lot of information on this webpage, but I think that's where my answer has to stop today.
Okay, well, great, thanks.
Okay, Michael? Question for Mike?
Yeah, so thank you for this very nice demonstration. So I have sort of a naive question because I'm not really familiar with Dask, although it sounds very interesting. So the workflow you laid out strikes me as being very similar to Root's R data frame, that you start with loading and then you define, basically the transformations you want, and then you want a histogram at the end, and then you execute it all lazily. And so, right, so this is obviously a Pythonic way of doing that versus Root's just-in-time C++ compilation. But I was curious if you had any thoughts on the relative advantages of doing it this way in Dask, like if there were either from a runtime perspective or scalability or anything like that.
Yeah, I would say before, I know recently, I haven't been as plugged into Root development as I was when I was a particle physics grad student, but I know that even our data frame can run on Dask now. So I think there's definitely a lot of overlap here. I would say, to me, the pure Python workflow here is something that I would have preferred when I was working on this stuff. I'm not, like I said, it's been a while since I've thought about Root, so I have a hard time speaking to the advantages that I would say modern advantages compared to back when I was using it. I was like kind of eager to be able to live just in Python land. So another thing I liked when I was personally stepping away from Root was just the PyData ecosystem as a whole. The ecosystem is designed to work. All of the packages are designed to work together. Obviously, Root has existed since the 90s, and it didn't always easily communicate with the PyData ecosystem. But as far as I know, I think that picture is improving. So that would be my personal feeling in that realm. In terms of runtime, I don't have any Dask versus our data frame benchmarks that I can cite at this point. But I dare say they exist. I have a feeling someone has looked at that. So yeah.
Thanks for taking the time. As I said, it was sort of off topic, but it's very nice to see that some of these features are available, as you said, in the PyData ecosystem as well. So thank you.
Mm-hmm.
Okay.
I could offer some comments if you like.
Yeah, please. If anybody has, absolutely, go for it.
Yeah, I just mentioned that. One thing that at least at first will be a bit different here is, since Dask is wrapping awkward directly, the granularity of the task graph will be much finer than I think with our data frame, because still the user supplied functions are sort of, let's say, at the level of doing a chunk of computation. There's only so much granularity that you can accept when the user supplies the C++ code, unless they start to do some getting into compiler kind of realm and start to partially compile the C++, inspect the AST, and somehow design a task graph. Whereas, if Dask awkward, as you saw each individual sign, hyperbolic sign and addition, and there's chances there in principle for some optimization paths to do useful things. So that is one example, I think, of a difference that will be, something we might be able to profit from. And then I'll just mention on the side that there is also at least a comparison between Coffee Awkward 1 and our data frame that shows at least a similar order of magnitude compute performance on
Okay, cool.
single core.
Okay, thanks.
Okay, thanks. Yeah, that's interesting.
Next question is from Angus.
Yeah, thanks for a great talk, Doug. I know a disclaimer ahead of time, this might have been something that we've discussed at one of the meetings I wasn't at. If so, sorry. I use awkward, I think maybe a little bit unconventionally, is probably a bit too strong a word, but I'm often working with early in my analysis, like signal data. So it's quite voluminous and it's also partially regular. And so I have a combination of high level awkward functions, ak.num and so on. And then I have chunks of code where I'm actually either passing it off to another library, or whether that's in the PyData ecosystem or not. And so I think one thing that I know I would want to be able to do with awkward Dask is the equivalent of like map partitions. And I know we've discussed that previously. I'm just curious with map partitions, so taking a chunk of the array and then that's actually being a concrete awkward array we can work with. Have we had any discussions about how that will then map into providing that meta information with like type tracer, for example? So do we need to consider a way to describe the result of a map partitions function without doing what we currently do for type tracer, where we invoke that operation with no data? Because I imagine for let's say that transformation is doing a Fourier transform, for example, trying to Fourier transform an empty array is not necessarily a well-defined prospect. So I would imagine you'd want to annotate your partition function with metadata, but I don't know if have we had any discussions about that, or am I barking up the wrong tree?
I don't say that barking up the wrong tree here. I mean, Jim, feel free to jump in here, but I don't think we've talked about having that style of metadata evolution. I would say there's there's room for it, I think, in terms of if there is demand and it's something we can do, we can absolutely look into it. Some kind of, as you mentioned, if one could pass some small piece of data in order to help with the evolution of metadata, that's something. Yes, we haven't discussed that in any of our chats, but perhaps it's something we can chat in the near future.
And I think that Nick Smith's comment in the chat, another also useful for Gordon's case of custom data loaders, is spot on. That this was the same distinction between from delayed and writing your own source. And the piece of awkward information that would be needed for this is the form, the low-level concrete type. So if you're familiar with form, well, Angus is familiar with forms, all right. That's the information that would need to be conveyed to Dask somehow. So maybe maybe if we had an interface for a black box function that's nevertheless takes a given form and returns a given form. That's the sort of thing that could address that, and also Gordon's data loaders.
Yeah. Martin and I were discussing at least in nothing in code yet, but just discussing how we could perhaps design an interface for doing this type of metadata definition from it being user configurable. So it's something we've at least begun to thought about.
Okay. So next question from Philippe.
Thanks for this nice talk and interesting demonstrations. My question is about file formats. So you in the demo you use JSON files, and you mentioned root and packets in your presentations. My question is how difficult it is to add support for a new file format in Dask.
Yeah, so that's this definitely has some overlap with what Gordon was asking about earlier. There's built-in support in the Dask ecosystem for quite a few file formats. There's Parquet and ZAR and HDF, CSV. There's a lot of existing engines for loading data. Each of them do have their own, most downstream functions for loading the specific type of file format. But there's absolutely some shared logic in Dask for doing this partitioned data loading. So it's not super difficult to add a new file format. I mean, at the end of the day, one could write, as I showed, a dictionary by hand or the delayed annotation, that example I showed. One can do that with any file format they'd like, as long as you have some function in Python to load that data. You can delay it. You can turn it lazy. So that it's something that is not super high hanging fruit in the Dask tree to do. So if there's demand for some file format and that we can add built-in support, it's not that, it's not that difficult of a task. I would say it's quite straightforward to get started experimenting with the delayed workflow, and but there are limitations to using delayed, and so adding built-in support, with a delayed example even would make getting started on built-in support much easier.
Okay,
Actually, on this, since the question did come up a few different times about the data sources in Awkward itself, there's the data sources have to be given. They have to be awk. From this and awk. From that. Except for uproot, which is a whole separate package. So I should say a few things about this because there have been so many questions. In uproot, there's a GSOC project, Google Summer of Code project, to add uproots.dask, and there's probably about 10 applicants so far. So that's a project that will likely happen. The other functions, awk. From JSON, awk. From Parquet, awk. From Arrow. These are just regular functions in Awkward Array that all of these functions should get wrapped by Dask anyway.
Right.
Yeah. So the only other ways to get Awkward Arrays are from Python iterables. So that's if we could get that from a Dask bag, that would be appropriate. And unflatten. Unflatten will take NumPy arrays and turn it into a jagged Awkward array. So if we have doc.unflatten to take Dask arrays, then I think that users won't be looking for a way to hand feed a new Awkward array because how they're getting them now is through these functions.
That's right. Yeah, that makes a lot of sense. Yeah, thanks for clearing that up, Jim. Yeah, sorry if I was a little confusing to folks about IO capabilities. Yeah, the plan is absolutely for us to support what Awkward supports. Yeah.
So there was also a question from Peter. Are there any other non-HEP users visible to Anaconda?
Oh, so yeah, Jim, you've actually introduced us to someone interested. working
for
on.
this, yeah, in this particular.
Yeah, for this particular, for Dask Awkward, there are non-HEP folks interested in Dask Awkward. Yes.
The one you're referring to is in Pangeo for
Mhm.
buoys floating on the ocean.
Mhm, mhm,
They have variable lengths, trajectories.
mhm. Yeah, and also there are folks within Anaconda who who are eager to use this for other things that are not high-energy physics related.
That's something I would want to know about. I didn't know about that.
Yeah, Stan is eager to use this for JSON processing, for example. Yeah.
Oh, okay.
Yeah.
I want to learn about that. Okay.
Yeah. I'll pick his brain a little bit more.
Are there other questions out there? We're I guess 5 minutes. Actually, we're exactly an hour because we started 5 minutes late. So other questions out there? Gordon?
Yeah, I mean, if there's nobody else, especially someone who hasn't asked a question already, otherwise I'm happy to ask one.
Okay, I'm not seeing any other hands.
Okay, this may be less an awkward Dask, but it certainly is connected with this ecosystem. There are times where in your demo you knew you had 50 files at the start, or however many files it was. But there are times where the files start coming in before you know exactly how many you're going to process. So it just makes some sense to just get started working on the ones that you've already got, and then adding more files as they show up. Is that something that is supported both by Dask and Awkward Dask?
There is a project that I have not worked with, but I know it exists. It's called Streams, and it's meant for this style of processing. Yeah, where you have data incoming. Unfortunately, I'm not sure exactly what the status of that project is, but I know that Dask was in mind for that project. I can do a little bit of digging and get back to you in the IRIS-HEP Slack on this project. But
that would be great.
Yeah, I can point that out to you once. Offline.
Okay, but to your mind, that's something that's separate from any of this stuff, this layer, right? That has more to do with the distributed part of the project or whatnot. Once you get the graph, then something else takes over and deals with streams or batches or whatever.
I'm not 100% sure about, but yeah. Nevertheless, I'll point you to the Streams project. Yeah.
Okay, that's appreciated. Thank you.
Mm-hmm.
I see that Lucas is back and he has a question.
Yeah, I had a question. So yeah, sorry, I was disconnected for a bit, but I did catch the demo and that was great. And so I have a question kind of related to that. So in the demo, you were reading back from Jason. So I apologize that this question was asked already. But so one thing that we we're playing a bit recently within Atlas is to try to analyze data through BigQuery, which is kind of this columnar database that is available on Google Cloud. Mm-hmm. And so that's kind of interesting. The way that we would do it is that we kind of do some kind of pre-selection using some SQL or like a BigQuery DSL, and that streams to us columnar data, and then we would kind of analyze it through Dask in a distributed way. And so I know that there's a kind of Dask BigQuery connector or something. And so can you maybe comment on, how this would mesh with Awkward or this Dask Awkward package?
Yeah, if there's, so kind of ignoring Dask for a second, whatever format you mentioned it comes through some columnar selection, perhaps a SQL query, the concrete form of whatever comes out of that. If there is a way to turn that data into Awkward, then there is absolutely a way to turn Dask's support for BigQuery to connect that to Dask Awkward, because that would just be stitching components of a task graph together. And that's absolutely up in Dask's lane. So I'm not familiar with Dask's support for that part of Dask support, but that I imagine just that the output node for that for whatever Dask operation for that cloud service could then be the input node for a Dask awkward collection.
Okay, yeah, I mean, that's what I gathered. I mean, like probably Dask awkward is not really connected to what the data source is, and whatever data source is supported by Dask in some part of the ecosystem should kind of work transparently with Dask awkward.
Yes, definitely.
Excellent, thanks.
Mhm.
Okay. Other questions? Because reminder, we're over time, but this could be last chance. Okay. Well, let's thank Doug again for this great talk and demo. And see you at the next IRIS-HEP Topical meeting.
Yeah, thanks a lot, Jim.
Thanks, bye.
Thanks, bye.
Bye.
Bye.